So go ahead and take it away, Garhan.
All right. So I'm Garhan Attebury with the University of Nebraska and the Holland Computing Center, as Jason said. It's still in progress, so not completed, but we'll see how that goes here. First, as soon as I press the button, I'd like to go to the next slide and kind of introduce the Holland Computing Center for those who aren't familiar with it. We are the group that is tasked to provide research computing for the entire University of Nebraska system and all associated collaborations, so international in many senses. We now have 3 data centers that we have a presence in. 2 of those are specific to HCC, and we just recently started moving into a campus central IT hosted one. Size-wise, we operate around 1,300 servers across 89 racks. I finally counted them up the other day. Networking-wise, we have on the order of 80 switches. That's Ethernet, so that's excluding InfiniBand and other higher speed interconnects. We offer 2 HPC clusters. It's kind of our primary resource. One HTC, so high throughput cluster for physics. We have an OpenStack cloud, one of our data centers, and various other things. We're a fairly small group. We have about 19 people. That's including our director and all sysadmins, application specialists, and undergrad and graduate students that work with us. We've been steadily growing, which is good. I want to emphasize too that we don't do enterprise IT stuff. That's not what we are involved with at the university. Those things are hard and they involve money and identifying information, HIPAA, all that. We leave that to the central IT group, which is called One ITS. They are very much an enterprise shop, and we are very much not an enterprise shop. We're academic research, almost entirely a Linux shop too. So with that gentle introduction out of the way, the 3 topics I want to cover include the first one, which was the data center upgrades. That's what I had in mind when Jason asked for contributions to this series. So that's what I'll focus on first. And then I will mention some of our decisions that we still have yet to make on this project as far as network architecture and how clever we want to be versus just making things work nicely. And finally, I'll talk about some of the, I call them quality of life improvements we've made, especially with respect to networking over the last year or so, and also while doing this upgrade project. So take a trip on the Wayback Machine. Once upon a time, we were a small, 1 cluster research group. We had a few Nortel base stack switches stacked together, cleverly enough, and a cluster that had a Marinette backend. It was all flat, layer 2 network, not even anything but the default VLAN. The only clever networking was like a head node for the cluster. NAT, and those were simple times. Everything was easy from back then. Eventually, we moved on to the big chassis switch era. That's partially because we became involved with the LHC project, so the Large Hadron Collider, and we became a Tier 2 US CMS site. And along with that was, of course, the promise of huge amounts of data and needing 10 gig WAN connections and all of those things. So we ended up buying a Foundry Big Iron RX16 switch, which I loved, near and dear to my heart. We had to let it go recently. At the same time, we actually inherited our Omaha data center, which is the PKI data center, Peter Kiewit Institute, that I'm going to be talking about mostly today. That data center had a supercomputer in it, and at the center of it was a other giant chassis switch, Force 10 E1200, and these were great at the time. Boatloads of 1 gig Ethernet, some 10 gig uplinks, almost entirely non-blocking. The Founder one I remember had 721 gig ePorts, all in one big chassis, and we didn't have to actually care much about how things worked. We maybe had a couple of VLANs to segment things out, but largely we just treated everything as you plug it in and magically you have networking, and you don't really care too much about anything beyond that. At that time, the university actually handled all of our routing at the WAN level, and we didn't. Then we move on to the don't be the last Big Ten school without 100 gig era. Thankfully, we weren't. I think getting close to that was probably where the money came from. We also happened to need more than 10 gig at the time. The physics project could easily saturate our connection to internet too, and 100 gig was what everybody wanted. Turned out that we also had some money up here at the time of the wonderful academic variety where it's spend this money by tomorrow, basically. We had been already talking with Brocade, and I had our eye on doing the MLXE router series. And so we bought one for our Lincoln data center for the physics project primarily, so we could have a 100 gig line card and do all of that goodness. And basically within a week, we turned out we had twice as much money, and we had to spend it basically that week again. And so I called the vendor up and said, give me another one. I think it was the easiest router sell they've ever had by far. So that's how we ended up with 2 MLXEs kind of as our core at each data center, which we've used for a while. We also started pairing with LHC1, which is with ESNet. It's LHC1 is an overlay used for the physics projects involving LHC. And we did that on our end, on our MLXE. And at that time, we kind of switched from the university helping with networking to we now treat them purely as our upstream ISP, and we do all networking and routing and everything internally to HCC. And at this time, when we bought these, we had plenty of 10 gig ports on them, and that was the answer to all of life's problems, was just throw a couple more 10 gig links at it and get your bandwidth, and don't worry about performance, because everything was not demanding anything more than a few 10 gig links. And it was all in our clusters, mostly still just layer 2 networks and easy button. So with respect to the PKI data center, this is a lovely PHP weather map, for those of you familiar with that I had made at one point to kind of diagram out the switches there. At the very center, you can see that MLXE. It's kind of our core, and then we just have a scattering of top of rack switches around it. The whole section on the top is one of our HPC clusters. Some of those are 1 gig top of rack switches with 4 10 gig uplinks. Some of them are 10 gig top of rack switches with 40 gig uplinks. On the left in the middle was a stack of 1 gig switches for an old cluster that's now been moved to our third data center. In the bottom left corner is the little triangle. That's our OpenStack cloud. Those are just, again, top of rack switches, but they're all 10 gig with 40 gig uplinks. And the new thing that we added in, I guess it's maybe a little over a year now, was a couple of petabytes of storage that, instead of being our usual method of doing storage, which was Lustre file systems, which all had InfiniBand and connected to worker nodes that all had InfiniBand, and therefore the storage all went over InfiniBand. This new system was going to be primarily Ethernet, because we wanted to mount it on all of our resources at all the data centers. And so it was going to leverage, the Ethernet fabric as opposed to InfiniBand. We'd kind of been able to be lazy in the past, because nobody, when all the storage traffic is over a high-speed interconnect like InfiniBand, and the jobs do that, there really wasn't that much demand for Ethernet. Then that changed with the storage. I have a quote here, and I actually think, Jason, if I remember, you were the one that said this, although I couldn't dig up the slide that I remember seeing of yours where you had this, and that's that researchers don't always know things aren't optimal or could be better. So here is a lovely, network bandwidth chart from an interface on some of our stuff. At this time, we had one researcher out of hundreds of active researchers saying, hey, my jobs keep dying. Why is this? Ultimately, it turned out they were doing kind of a nightly cron job to download weather data from NOAA, I believe. And, they expected their jobs to take an hour at most. They submitted these essentially wget jobs into our batch system. And normally they'd go and take minutes at most. But now they started failing, and eventually I had to look into this and figure out what was going on. It turned out they were getting on the order of 10 kilobytes a second, maybe, whereas opposed to getting full gigabit speeds out to Internet 2 before. And that's because our storage links had been saturating the network. At the same time, the person who was actually causing the saturation from this new storage and everyone else was saying, hey, this stuff is great. This is awesome. So it's a nice highlight of researchers don't necessarily know that things are in a dire state or could be improved. Looking at that PHP weather map, this is kind of what it looked like on a daily basis. Over towards the right there, you can see those links that amusingly, because of how SNMP counters work and how the PHP weather map shows it, end up being over 101% utilization on those links, clearly on fire and bad. And those are the worker nodes off those top rack switches where the researcher was having problems. Our quick solution, of course, was, well, we'll just limit the storage by removing, one of the 4 10-gig links and make it a 30-gig link. And the, connections going up to that 1738 kind of switch there in the center of the top, that was 4 10 gigs as well. And so, arbitrarily limiting it, so no real chance of it saturating any given link to a switch. And of course, we could just throw more 10-gig links between the switches, and we kind of did that for a while, but that's not sustainable by any means. So, the easy solution on upgrading this and solving this problem was you buy modern switches and you have faster links. It's kind of the easy fix to bandwidth problems. Unfortunately, we're very much have the academic funding problem when it's never the money there when you want it until all of a sudden it appears. And it did around this time with the usual, have X number of tens of thousands, actually it was hundreds, I believe, at the time, dollars, we need to spend it in 2 weeks. So this urgency thankfully let us spend some money and get not 1 but 2 new core switches. And it's kind of silly in my mind that we have the money to buy the hardware before we have a plan on what we're going to do with the hardware, but that's how it worked out. And it's kind of repeats that like that every now and then. At the end of the day, we bought 2 of Dell's Z9264F switches. So these are 2U switches that have 64 100-gig ports in them. You can, of course, break those out into 25s or 50s. Almost all, actually exactly all of our existing infrastructure was 10 or 40. You can do that too. There's a caveat where with the Broadcom Tomahawk 2 chipsets, at least, that these have, if you use one of the ports and you break it out into 4 10-gig links or use it as a 40-gig link, you have to sacrifice the port next to it. But still, at the end of the day, 2 of these provides a lot more ports and enough capacity for us to go a long ways, I think, into the future. So we did buy those, and in my opinion, we actually had a fairly good deal price-wise on them at the time. This was back before the end of last year, calendar year, when they were first available. And that money monster is tricky. It turns out that as soon as we purchased those and we're thinking of, okay, let's get all of our, upgrade our fiber infrastructure at the same time, the money disappeared. It's one of those, spend all of our money for us. How dare you spend all of our money for us? Stop spending our money type of conversations. It was rather entertaining. But we've managed to since find some more money to buy, cabling and do that, which we do ourselves internally with HCC. This is, I think, great for flexibility. It served us well over the years to not have to wait for campus cabling plant guys to come over and make a change. At the same time, though, we're a ragtag team of academic HPC people who don't really have necessarily a set standard or guidelines on how to do things. And we're also still kind of new to doing fiber, especially when it comes to MTP cables and doing fiber patch panels. Most of what we've done in the past, just because of the nature of building HPC clusters is use copper cabling. And so we're stepping a little bit out of our comfort zone. So the PKI data center, this is kind of a top-down view of what it looks like. There's 4 APC in-row cooling pods. There's a picture in the bottom right there of one of those pods, kind of give you an idea that it's, rooms inside of rooms. At the bottom is the, our networking area where we had our MLXE router. And that's where we put our new Dell switches that we bought. And then you can see there on the text on the right, I have kind of the count of how many top of rack switches were in each of those other pods. The top 2 were mostly all 1 gig connected hosts for one of our HPC clusters, and all the newer stuff has been going into the bottom 2 pods, which is why there's all the 10 gig top of rack switches down there. If upgrading this, we actually get to recover one of the 10 gig top of rack switches that's in pod 2 there, which is why I marked it as recoverable. Size-wise, I did the math, and turns out, even though we're not quite using all of them, but we're pretty close, there's 432 10 gig ports and 672 1 gig ports across all of these switches at the moment. And to keep in mind, too, this doesn't include our InfiniBand fabrics by any means, or the out-of-band management network we have. So we had to figure out how we were going to run cables between these, and ultimately ended up deciding that if we were going to try to build out a leaf-spine architecture connecting our existing top-of-rack switches back to these new core switches, for the first 2 pods, it makes sense to just do active optical cables. So these are, 40 gig transceivers, and they've got built-in optics. So they're, from a physical side, nice to work with because it's fiber, not giant, 1-inch thick copper cabling. And we chose to do those down there. And then for the top 2 pods, it's all 10 gig uplinks on the top of rack switches there. So we figured we would find a way to provide patch panels and, have 10 gig ports going up there. And so to do the top of rack switches for those top 2 pods, kind of settled on this method. You can tell from the watermarks that we bought all this stuff from fiberstore.com. Turns out you can buy cool customized trunk cables. In our case, we bought 48 fiber trunk cables, which ultimately end up being 4 12 fiber MTP connections bundled together. They're kind of wrapped in a nice little mesh. You can customize them in all sorts of ways with various breakout lengths and all of that. The ones we bought, we needed a 20-meter one to reach that first pod and a 15-meter one to reach the second pod, and essentially it gave us 4 MTP connections between them. If you remember back at the previous slide, there were only 6 top-of-rack switches in one of those pods and 5 in another. 6, if we do 4 10 gig uplinks to the switch, that's 24, essentially 10 gig connections we want to make. So LC pairs. So using these little cassettes that you see on the right, which take those MTP cables in the back and provide an equivalent, the 6 cables, 6 LC ports on the front, we managed to do that in order to get our connectivity between the pod, the rack with the new switches, and the pods at the far end of the room. This probably isn't the cheapest way. You can do all sorts of other ways, but this was certainly better than pulling at least 44, LC fiber patch cords across the top of racks that are already ridiculously messy and have heavy copper cables scattered all over them. These MTP trunk cables from Fiberstore turned out to be quite nice to work with. So this is kind of, again, the idea there. You can see the bottom pod. We bought a 2U little fiber cassette enclosure to put these cassettes in. On the bottom right picture, you can see what it looks like now that they're all connected. All those cables you see coming out of the front are essentially 40 gig to 4 by 10 LC breakout cables. So you can imagine the other end is going down to little 40 gig optics that are plugging into our new switches. And then they come up and plug into these little cassettes. From the back of the cassette, you can see those MTP connections, which go to those big trunk cables, and they go up and across their pods all the way to the far end, where they come into what's kind of hard to see in the picture, the top right, but a little 1U kind of panel to plug the cassettes into, and then provide our 10 gig connections there, where we can just run short 3 and 5 meter LC patch cords to the switches. There's, of course, 1U, nicer chassis that you can buy for mounting fiber cassettes and different style of fiber cassettes. This one set was chosen just because of the physical constraints we had with some of those, as you can see, large bundles of copper cabling coming down from the existing cluster install that's in those pods. The physical cabling for this is mostly done. We have a couple of those active optical cables we still need to buy just to provide full, not necessarily non-blocking access, but close enough to our new core switches. It's entertaining, I think, to do all of this ourselves. You can see some of the examples of what Cruft builds up over 5 years. The bottom left picture is a lot of InfiniBand optical cables. That's between IB switches. To the nodes, they're actually copper cabling. Buried in there, you can see the mess of even more pictures more LC cables that I threw in. And on the right, I'd like to present the officially licensed fiber pull-in mechanism. Yes, it's a Swiffer. No, I'm not proud of that. Maybe this is what we get for doing our own cabling versus having proper tools and things. But a Swiffer actually turns out to work really well for moving little coils of cable, because you can rotate it to keep the cables on and then rotate it the other way to make it fall off nicely. That's why I like to include that picture. So with the cabling done, this kind of brings us to the next section, which is essentially planning for the future and what kind of architecture we want to do here. We could just stick with what we've had, or we could choose to improve it. And so I'm going to go over a couple of the decisions we're in the middle of making still. So in order to kind of make architectural decisions, it helps to know what our PKI data center means to HCC. It's by far the best data center that we have out of the 3 options. It's got the best power. There's a full room UPS. It's got generators. It's also the most likely to be upgraded with respect to cooling and power, and therefore become more dense, as opposed to our Lincoln or the campus data center. Partially because our Lincoln data center, while it has the most physical space, is the next thing to be probably demolished when athletics gets a lot of money and wants to renovate the stadium. So we're choosing to not invest into the infrastructure there. Also, our main HPC resource is located in the PKI data center. And as I mentioned before, we've added storage there that's common to all of our resources. So increasing reliability would be nice. You probably remember the little single point of failure, all the things guy in the bottom right on our weather monitoring graphs. That's because there is no redundancy or reliability at the network layer right now. And finally, there's our Anvil OpenStack clouds up there, and that's largely going to be where I expect multi-tenancy needs to increase, and new environments, and wanting to do maybe network research with various technologies like Kubernetes and other cloud native technologies. All that's probably going to become realized at PKI. So we need to increase our flexibility at the networking layer too, not just have a single layer 2 VLAN across everything that is hard to share amongst others and segment accordingly. So the downsides to the existing architecture, I kind of hinted at that. We don't have any real redundancy, a lot of single points of failure right now. And that's worked for us with a academic HPC. We tend to ignore redundancy. If you can buy more compute nodes, you do that rather than buy 2 switches, because we can afford to be down for a day or 2. And that still holds true, but as we grow and get more offerings, that we have out to our users and just have more users in general, at some point we have to try to make decisions on being more reliable and robust. We've been burned by big layer 2 networks in the past, like a lot of people have. Yeah, we can run spanning tree on these things, and of course we do, and usually we don't do it right. And we've had many times, 3 at least that I can think of, where spanning trees have been an issue. One particular time I recall was clever students who were working on a cluster of their own. It was a student-run cluster. Somehow managed to hide a 100 megabit switch underneath our raised floor in one of our data centers, which took me about 3 days to find, and caused all sorts of entertaining little hiccups. There's also right now no real segmentation with resources, with everything being a flat network. Yeah, we can do IP tables on hosts to, do kind of a security front, firewalls and things like that. But a lot of times I think it would be nice to be able to do that at the network layer, with ACLs on switches or routers. And at least some of our previous hardware, I know the Foundry, for instance, you couldn't have active, layer 3 ACLs when it was doing inner VLAN routing, within 2 different VLANs on that switch. So a lot of times it's nice to have separate layer 3 segmentation in order to do those things. There's also, of course, the ARP problem. Big layer 2 networks are bad. Nowadays, technology is good enough that I'm sure you can cram 10,000 hosts onto a single segment if you twiddle all the knobs correctly and the hosts are fine. Probably still not a good idea for the most part. In our case, we're a Linux shop. Linux has a hard limit of, by default, of 1,024 entries in the ARP table. We already have to twiddle the knobs for that because we have more hosts than that at times, especially if you include things like VMs and other interfaces on the hosts. We do that on multiple clusters at this point, and it's just one of those special sauce knobs that it's easy for us to add, especially with config management, but at the same time it's working against default configuration, so it's just technical debt that we accumulate. Another bad one is network research projects. We're tasked to provide research computing, and whether others that work with us like it or not, part of that includes networking research, and we've had very valid projects with NSF, CCD&I projects, where we've wanted to play with SDN in the production networks. And we've had one long round of fun over the course of many months where we were doing ONOS SDN controllers and tying that in with our production physics network, because we wanted to actually operate on the production traffic, do some steering and traffic prioritization. And that's great and everything. And despite how careful we tried to be, with doing ARP proxy in order to just get traffic to flow from one point to another, we managed to break it and blow it up multiple times. Having switches at one end of your data center that should never see packets from another, all of a sudden seeing them, or seeing our MAC addresses appear on one side and then not the other, and it was quite chaotic and messy. Hard to do when your only way of operating is a giant flat network segment. If everything was segmented out, we could have done it in a little smaller environment and maybe not had quite the blast radius for the disasters. So we have to think, how far do we want to go? How many nerd knobs do we want to turn, and where do we stop? I listen to a lot of, networking related podcasts, and I'm not a network engineer by trade, but I like to keep up on it, and all of the latest, modern technologies that people can do and you can buy sound great. You can have big orchestration tools and make really flexible and elaborate and automated networks, but we really probably don't have a need for most of that, and we also don't have a networking team to run any of it anyway. We could do something really in line with our daily lives, which is Linux sysadmins. 7 of our staff are Linux sysadmins by trade. I like Cumulus Linux. That's a very popular network OS now, and I've looked into it a lot. We've talked with them many times, but it turns out they like to feed their employees, and therefore that costs money. And it's kind of prohibitive, at least right now, with our funding cycles and when we get money and how much it would cost to do that for our scale and their ongoing licensing costs. We could do open source everything. There are great things out there that are being looked into by the LHC projects and CERN, for instance. Juniper's Contrail. There's also an open Contrail, I know. And we could develop tools in-house, but again, it's time and effort. We probably shouldn't. But we can at least maybe move away from the flat layer 2 design and become a little more flexible. So a quick survey of our options. We could do a flat layer 2, I mentioned that. That'd be along with the idea of we just continue as is and we don't change things. As an example of don't change things, the MLXE router at this PKI data center is still set to only a max MTU of 1500 because changing that requires a reload, and we haven't reloaded it in a long time because it's very disruptive as everything runs through it. We could do some layer 2 resiliency options. We bought a pair of these Dell switches. We could use VLT, which is Dell's virtual link trunking, similar to MLAG. I think Cisco, it's called VPC. I'm not a Cisco person, so feel free to type in the chat if somebody wants to correct me there. And that way you can have a pair of switches that's, as far as devices are concerned, it's all layer 2 and nothing terribly fancy, but you do gain some redundancy that way. The middle option, you can see it's bolded, therefore probably what we're doing, as you might guess, is move the layer 3 closer to the edge. So do layer 3 on leaf switches. It's not too big of a change. We already do some routing internally, OSPF within HCC and BGP pairing with like LHC1 and our campus and other places. So it's not completely foreign to us. Could do the crazy cousin of the above and go routing all the way on the host. I proposed this, and I know it works because we've done it in some test environments, but one of our other people who works with us pretty much gave me the no, just no look. I didn't actually have to say the words. I could tell by the look on his face that was going too far. The commercial solutions, again, we don't really have money. We're not entirely a Dell shop, but networking-wise, largely we have more Dell switches than anything else. They just, I think, partnered even more with Big Switch Networks. So that would be an option, but it's also an expensive option. So not going to happen. And again, we could do things ourselves, but probably not worth the effort at this point. I drew some pretty diagrams to maybe explain these options to people who aren't necessarily familiar with it. You can Google for spine leaf and layer 3 to the edge, and you will get a lot of blog posts and documentation if you're curious of what it actually means and practical examples. But I'll just run through my little pictures here real quick. So we could just do use one of those new switches we bought, that kind of, what is that, cyan colored one there in the middle. Run that to the leafs and just be layer 2 exactly like the MLXE is now. It's simple, but again, we've already said that's really not an option because we do need to improve how things are architected at the moment. Next option might be that we do the VLT, like I said. So this is kind of a layer 2 aggregation with the switches to get redundancy. We could do it at the rack level 2. For instance, I mentioned we have that storage that's important now. Maybe we want to actually have a second pair of switches there for that rack or the nodes that have storage. We could tie it all together this way. It's a little bit with vendor lock-in, at least within a pair of switches. You'd have to have the same exact switches. You do still have layer 2 all over the place. It's tried and true technology, but I think we might not choose that at the moment. Instead, go for something like layer 3 all the way down to the leaf switches, so the top of rack switches. So, in our case, it'd be you have all of your interconnects between your spine and your leaf, but there's no layer 2 magic like VLT there. Each leaf is where you're advertising whatever subnets, and we probably advertise /24 for v4 subnets and /64 for various IPv6 subnets, and you advertise those up to the spine, and any switch can talk to any switch. One hop, it's all layer 3 routed. It's really easy to troubleshoot those things and really easy to maintain. Traceroute actually kind of shows you your physical network topology even to an extent. So it's nice on a lot of fronts. In the rack itself, we would probably still just stick layer 2. And for my diagram, it's one rack per one leaf. Really, we'd have multiple racks under one leaf, and there's some really weird edge cases that we'd have to deal with, but it's not too bad. One thing is we'd have to rework our IP address scheme to do this, but that's not a big issue. You could also integrate VLT into this. So like I said before, with the storage rack, maybe have a pair of switches there, but they act, as far as anything else is concerned, as a single switch, and therefore we can still do layer 3 between leaf and spine. I mentioned ECMP over there. That's equal cost multipath. Probably do OSPF internally. Could be BGP. We haven't made those decisions yet, but we hope to soon. Basically, any link path to another one is the same cost, and therefore you gain redundancy in the sense that if one fails, it goes away and the routes get removed. And also you gain speed because you can balance over them. It's also nice because if you want to do maintenance, you can just manually tweak the weights on the routes, and you can pretty easily verify that, yeah, my traffic is no longer on this switch. I can now take this switch out, fix it, upgrade the firmware, do whatever. It's quite flexible. The far one that we won't go to, I think, is, of course, that layer 3 to the host. I've done this in a test bed with IPv6 only hosts where Docker containers were actually being started by our job scheduler Condor, getting their own IPv6 addresses, advertising those out to a leaf switch, which then went all the way through our network and got advertised into the core in the university. And it's fun and it worked, but it's crazy complex if you don't have a some big application or a controller running this all for you, and we don't. And so I think going that far is a little too much. So we're probably going to do the layer 3 to the leafs. I think this is going to be an iterative rollout. I've talked through it with a few people that work with us here. With the re-IP things, it's fine. Some people don't like that change, but honestly, if you want to scale, you can't tie IP addresses to a physical location, and it's all computers. You can script everything away at the end of the day. Probably do /24s for most racks, have the outliers of IPs. And then, of course, doing this does add some complexity on configuration, and it'd be nice to have this automated. And so I think we're going to, at the same time, we need to improve our tooling in order to let us do this. And that brings me to the third and final section that I want to talk about, which is kind of making all of this sustainable and tolerable. So I think within HCC, this is kind of what our current tooling kit looks like, at least just focusing on the maybe network side here. Obviously, we have a lot of other things we do, but all our provisioning is done via Cobbler still. We've stuck with that for a long time. It's a network provisioning thing with to let you do PXE boot easily. Also kind of, in our case, doubles as an IPAM. That's where our DNS and IP addresses all come from. We do Puppet heavily for configuration management for Linux servers, which is great. It's not so popular for networking. There was a time where vendors were offering Puppet on their switches. Dell, I know, did that. It's definitely kind of fallen out of favor, I think. Ansible is, of course, a really popular one. I know we've had some talks about doing network automation with Ansible on this series before. And we use Ansible here and there, but not for networking yet. So we're going to still be sorting that out. On the monitoring front, just in the past year, along with this data center upgrade, we've finally, I think, settled on some better tooling and gotten everything monitored and put together nicely. We use LibreNMS for kind of network monitoring, graphs, and alerting. Oxidized is our config backup for switches. Most of our interaction with switches is still, SSH command line, but having Oxidized is nice for that. We do flow monitoring with ElastiFlow, which is an awesome product. If you haven't looked at that, you should. Could have a backup for flow data, which is NFSen NG. It's a new interface for the old NFDump tools. And finally, CheckMK, which is a pretty popular, Nagios type equivalent. There we go. I think there are things that we can improve that I've decided on while we've been doing this project is inventory asset management. We're actually really bad at that. Most of our asset tags that the university cares about, get mapped to a location and a device at the university, not within HCC. So I can horribly maintain spreadsheets that aren't really under our control. And while we've never had a problem with any audits or anything before, I think we definitely need to improve that. Same goes with our documentation for infrastructure, like where cables go, what power outlets are plugged into what. I've kept text files that show what PDU outlets servers go to, so I can power cycle them remotely if I need to. That's really horrible way of doing it, and I usually find more errors than I do answers these days, even though I'm the one that put them there in the first place. And finally, network automation. We don't have a good source of truth. Cobbler can kind of act as that, but Cobbler is meant for Linux host provisioning. It doesn't really, offer you a place to put in asset tags or other stuff. You can try to use it that way, but you're just fighting a battle in the wrong direction. So on that topic, just in the last 3 weeks or so, I started playing with netbox. I heard about this a couple of years ago when the guy that wrote it, who works DigitalOcean, put a thread out on Reddit, our networking, saying, hey, here's a thing. And I've seen it come and go on there as a topic every now and then, but I hadn't dug into it until very recently, primarily because I wanted to see if I could use it to help map those fiber cables that I was scattering amongst racks. And it turns out I could, which is good. If you haven't checked it out, I would suggest it. We're certainly in the evaluating point, but I think it's got a very good future potential here. For example, on that cable tracing I mentioned, there, the top left there, those would be, once I had all this stuff entered, the interface list for those Dell switches we bought. You can see a ETH113:1, so that's a one port that's broken out into 4 10 gig ports. That's what the interface name ends up being. If you have your devices and you could model patch panels with port mappings on front and rear, connect it all together, add the cables, I can click on that little blue button in the middle and go to a page that's a cable trace, which in this case, there's only 3 cables involved, but all the information is there, and it's actually really convenient and easy to look at. I can tell where the device is on one side, the actual Ethernet port, all the way through what front port label and rear port labels are, the cable type, the cable length, you could put a serial number on cables if you want into it. We don't do that, but you could. All the way to the other end of the switch in the bottom right there at the far pod, it's a 10 gig top of rack or 1 gig top of rack switch with one of the 10 gig ports. And playing around with this, I think it's actually really flexible. It's the people involved try to not have scope creep, but it does let you model pretty much anything you can think of. You could do big chassis switches with line cards like our MLXE, and connect cables to all the ports. You can model PDUs, so I can get the PDU outlet numbers, and the servers can all have what outlet the power supply 1 connects to, what outlet power supply 2 connects to. You can model all of this in this netbox system, and it's, in my opinion, from spending 3 weeks or so with it, it's very nice. It's not a big bloated, annoying commercial type solution where you're fighting it at any point. I think it's got a good balance at the moment. With that, it does include full APIs, which is kind of the win button for us. We might use it, for instance, we can take all of our information out of Cobbler and put it into netbox. So we have our hosts in Cobbler already with the interface names, on the servers, the MAC addresses. I've already done this with the API. You can pile it in. It works. Switches, we could do the same thing. MAC addresses off switches. You could automate the creation of your data that way. We could take our LLDP data out of LibreANMS to make sure our switch interconnects are correct. And that's kind of a way to populate netbox. I've written the scripts that do this, so I'm kind of happy that it can work. I just haven't done it at scale yet. Once that's there, you can also do it to maybe verify and audit that what netbox has matches the real world. If you could have a regular auditing or polling that says, hey, this switch port over here has the wrong MAC address on it. Somebody should go fix this and correct the information. So eventually, if you can get it populated enough, I have a feeling we could use it as a documentation resource, especially for cabling would be nice, and just asset tag management. So now that we have stuff scattered across 3 data centers, we don't have to rely on a human to go visually inspect the thing at a data center and say, oh, yes, this is where this device is and how it's connected. It'd be nice to have that in a system we could all use. And I think if it's ends up being a real good source of truth, that you can use it to further our automation. So some ways that might work is we could generate the configs for switches more programmatically out of using the information in netbox. When I thought about doing this 3 weeks ago was because I listened to a podcast from Packet Pushers. They were talking with some of the people that work at Roblox, a big game company, and they use netbox as their source of truth for generating all of their switch configs. And they do it, and I think their workflow is something along the lines of you generate a new config when you make a change, compare the diff between the new config and what's actually on a switch, and you can approve, yes, I want to make that change or not. So there's some options there. And it's be partially a human thing to make this work and maintain it, and a workflow change. Anytime we get a new device, we should add it to this and reflect it there first. And maybe we'll even get to the point where we unbox a server, somebody can put the information in netbox, and you can have webhooks that call out to other scripts. So we could potentially keep using Cobbler as our provisioning and DNS system, and just have netbox go ahead and call the Cobbler API to generate a new host and take care of all of our provisioning stuff that already exists, so we don't actually have to retool any of that. I think it's got a definitely good future here. Of course, obligatory XKCD comic picture of automation. Hopefully the bottom isn't going to be the reality, but it probably will. We'll see how far we get. If in a year's time we love this and have a huge automation framework built off of it, I would happily give a talk on how that all worked out for us. So to recap, time and science caught up to our old network, so we had to upgrade that. We got money and ended up getting 2 new switches. We're still working on our architectural decisions, although I think we're pretty set on doing a spine leaf, with layer 3 to the leaf type of a setup now, just because it's simple, it's cheap, but free, and it gives us the flexibility that it's the next step up from our current situation. We're good at network monitoring, but definitely lacking with respect to asset management and especially documentation. And so we're investigating netbox as a possible data center information management solution to remedy that, and we'll see how that goes. So at this point, if anybody has questions, I will happily answer them.
All right. Well, thank you so much for going through that. A lot of good information. We had a couple questions come in when James was mocking your Swiffer. First question: do you inspect the fiber connectors with a microscope before mating? And that also mirrors a question that I have: is what sort of level of cleanliness are you going to be doing as you repurpose and get all your new fiber infrastructure in there? How deeply are you going to be doing the cleaning and making sure that everything is looking okay?
So I'm going to preface my answer and say that I have read that wonderful, I can't remember now, is it Swiss Network? There was a wonderful European site, research or network, excuse me, a research center who had a great blog post on, fiber cleanliness and all of the horrors. And I have a great appreciation for doing that and keeping fibers clean, but right now we actually don't. I mean, we have little LC fiber cleaning pens that we use whenever we're moving stuff. Well, I won't say whenever we're moving stuff around. Sometimes when I've been doing all this recent installation, yes, I did that. By and large, over the last 10 years, in our experience, we actually haven't had too much issue with cleanliness and fibers being dirty and going bad. That's not to say it doesn't happen. Of course it does. But we are very much slackers in that category. And so, no, I don't have a microscope to inspect all these fibers. Most of the fibers that we're dealing with are, of course, multi-mode and short runs. This might change because you deal with LC patch cords. I mean, they're like $2 for a patch cord, and the optics are, super cheap. If they get dirty and they fail, then that's bad, but the cost of, losing one here and there is also really low. Sometimes it's cheaper and better time-wise to just pull a new one out of a box. With more expensive cabling, we're dealing with 100 gig optics potentially now, and, MTP cables, cost has certainly gone up, and I think we're going to have to actually care more about that in the future.
Yeah, I'd highly recommend just get a couple of click pens, cleatops, all the various pieces there, and just get into the habit, because what I found is that even if you pull it out of the bag, it's not necessarily clean.
Yep,
and that could really cut down on the debugging. So second question that came in was, have you done any of the LLDP from LibreNMS to netbox work yet?
Only in practice with manual. I don't have anything on GitHub for you to look at, but if you want to shoot me an email there, my address is at the bottom. I will happily share that when I get something there. The on that front, I've also done with some just straight Python before, and this was from a different project. Dare I say, scraping of the LLDP information from switches themselves. So that's another method of getting that.
Okay. James has another one. Elastaflow and NFSen, or ultimately Elastaflow and NFDump for depth.
So I thought about getting into that, but then I figured I was going to really blow through time and have scope creep on this presentation. Right now we used to use NFSen, and so that was kind of we had it around for a long time. Elastaflow is great, but it comes with the pains and frustrations of having to run Elasticsearch, and right now we're at least using Logstash for ingesting things, and I've gone through a lot of more pain and suffering than I care to admit in order to make it scale even to our relatively small number of flows from our core devices. The reason we have NFSen, or excuse me, well, it's NFDump is the thing actually capturing the data. NFSen NG is one of the newer. It's a new front end to replace the old NFSen front end. The reason we keep that around is because that's really lightweight, and it's easy to have. We don't drop packets or SFlow packets coming into it. It's small on the disk usage. The downside is NFSen NG. I'm not very familiar with it. I mean, we've played around with it to the point that I know that works, and it's kind of like, yeah, we're keeping this as our backup and longer term storage of flow data. If I'm ever looking at flow data for a need, I usually look at Elastaflow, and it's great. But right now we're actually purging all of the flow data from Elastaflow after about a month's time. So it's not great in the long-term storage front. sure some people use it for that, and maybe people can scale it out better, but that's been our experience now. So that's the reason we run both of them at the moment.
Okay. Well, I will thank you again. If anybody has any other questions, type them in. I don't have any more. So thanks again for giving this talk. Really interesting. And thanks to all of our Exceed and Campus Champion friends that joined as well. It looks like we have a lot of new names on this week. So glad that we got a lot of new people here. I will get this posted, and please send me your slides. I'll make sure that I put those with the presentation. And next week's talk is going to be from Globus. Rashna is going to be talking about the high assurance features for managing protected data. So I think this is a part of their new protected data piece that came out with their last release. So thanks again to everybody. Have a good weekend, and we'll talk to y'all soon.